Hello, in this module we'll be talking about the graphs of sine and cosine functions. Could be rather lengthy, so hang on tight. So let's begin here. So these are the trig functions. F of x equals sine of x, f of x equals cosine of x, f of x equals tangent of x. And so the cosecant x, secant of x, and this is the summary of the 6 trig functions. And we're going to concentrate today on this discussion only on the first 2. All right, so here's the graph of y equals the sine of x. Now I create a t-chart, okay, gave you some values for angles and show you what the output is and created the ordered pairs and graph them. So if we let x go from 0, some arbitrary points from 0 to 2 pi, if we put 0 in for the sine of x would be 0, so that's the sine of x will go through the origin. Another key point is at pi over 2. Pi over 2 comma 1. Sine of pi over 2 is 1. So you go over to the right, pi over 2, up 1. Another key point is at pi, and the sine of pi equals 0, so it goes back to 0 again. Another key point is at 3 pi over 2. Sine of 3 pi over 2 is negative 1, so we have an ordered pair at 3 pi negative 1. 3 pi over 2 at comma negative 1. And then 2 pi, we go back to 0, and that's 1 revolution around the circle, and we're back to where we started again. So you're like, well, what would happen if I keep going? Well, sine is periodic, meaning that it will repeat itself after 2 pi. So what you're seeing here is one cycle or one period of the graph of sine of x. Now we plotted some additional points just to show you that it is smooth and rounded. So we put pi over 4 in there, and we got 1. We got square root of 2. Well, we could put pi over 6 in there and got 1/2. And we put in 5 pi over 6 and got 1/2. And so we got some additional points just to show you that it's smooth. So this is one period of the sine curve. Now, like I said, it is not the whole graph. This is only between 0 to 2 pi. If you want to see a little bit more of the sine curve, here it is a little bit farther along. But if you notice past 2 pi, it just starts its upward flight again, and it starts coming back down after your 5 pi over 2. So it's a sine curve, it's just a wave. And it's just a wave that continues on, and it has that shape. So let's look at some properties of the sine of x. The domain is the set of all real numbers, which makes sense because there's no vertical asymptotes. The range consists of all numbers between -1 and 1, inclusive. Remember, say there's no y values that are lower than -1 or above +1. The sine function is an odd function because it's symmetrical to the origin. So remember, symmetrical to the origin basically means if you turn the graph upside down, it has the identical shape, and this is what would happen. So if you rotate that 180 degrees, the part that's in the, well, we don't call it, it would be down below the quadrant negative pi over 2. If you turn that up, it'll be back up in that first quadrant area. So the valley, in other words, will become a peak. So, all right. So the sine function is periodic with period 2 pi, because at 2 pi it starts over again. The x-intercepts, well, you can just look at the graph and tell what the x-intercepts are. 0, pi, 2 pi. So it's going to be multiples of pi is what they are. And the y-intercept is at the origin, 0. So the maximum value is 1, and it occurs at the odd multiples of pi over 2. So like pi over 2, let's see, pi over 2, well, and then that's the maximums. Maybe pi over 2, 5 pi over 2, 9 pi over 2. And the minimums occur at 3 pi over 2, 7 pi over 2, and 11 pi over 2. We call those extrema, and so we call those the odd multiples of pi over 2. But some of those extrema are maximums, and some of them are minimums. So the last part is important, but I would say just kind of know the shape, and you can't go wrong there. Alrighty? All right, let's look at some more of this. Graphing of y equals a times the sine of, that's an omega, x. They're using a Greek letter here. A lot of textbooks that you see they will use bx, a times the sine of bx. This author decides to use a different letter, and he's using omega. It's a lowercase omega, and so that's what we're going to concentrate on this. We're going to be using transformations for this. So we're going to graph y equals sine of x using transformations. So what does the 5 do to the problem? Remember, that's just a stretching factor, and we call that the amplitude. So the amplitude here is 5. So it just basically changes the height to 5. And we use the graph to determine the domain and the range of this function. So the absolute value of a is 5, so that's what we call the amplitude. It's the stretch. The period is 2 pi. And this is called the phase shift. Now, phase shift we're not going to refer to much about right now. Basically, a phase shift is a horizontal shift. And we're not going to talk much about the phase shift at this point. That comes a little bit later in chapter 5. Right now, we're just going to say the phase shift, which basically means the horizontal shift doesn't happen. It stays put. So I put that there for future reference. Alrighty? And so here's what the graph will look like. So it looks like a typical sine graph. Starts at 0. The first quarter, it reaches its highest point. Midway, it goes back to the x-intercept. 3/4 of the way, it goes down to its lowest point. And all the way to 2 pi, it goes back to 0. That's what sine curves do. But if you notice, the first quarter at pi over 2, it reaches not 1, but up there at 5. So that's basically a stretch factor, or what we call in trig function sine and cosine, the amplitude. So it's 5, its highest point, and at 3 pi over 2, it's its lowest point at negative 5. And of course, the domain, of course, is all real numbers, and the range is no longer negative 1 to 1, it's negative 5 to 5. Because the lowest point is negative 5, the highest point is positive 5. All right, let's look at another example, very similar. The y equals 1/2 sine of pi x using transformations. So first of all, there's your function. The amplitude is 1/2, so this time it's going to be compressed, not stretched. So the amplitude is 1/2. The period is 2 pi over pi. The number in front of the x is the omega. So it would be 2 pi over omega. So it's 2 pi over pi, which is 2. Now, what is 2? Well, it's 2 radians. 2 radians. Well, what's 2 radians? Well, you remember 1 radian is about 57 degrees. So 2 radians would be around 114 degrees. So if you want to get something a little bit more familiar to you, you could convert it to degrees. I wouldn't really recommend it here, but 2 radians is where it will start over again. So every 114 degrees plus or minus. So that's the period. Again, the phase shift is still 0. Again, we're going to leave that there. We're not going to touch it. It's not moving left to right. There will be a point a little bit later in chapter 5 that we do talk about the horizontal shifting left and right, and we call that the vertical the phase shift. So so just hold that one. All right. So there's a sine curve. It looks the same shape. Every time I graph one, it looks pretty much the same shape. The only thing different is the scale. Instead of having a height of 5, like the last example, this has a height of 0.5 or 1/2. Its highest point is the first quarter. Well, what's the first quarter of 2? Well, it's 2 radians. If you notice, all the way to the end is 2 radians. So in the middle will be 1 radian. So 1/2 of a radian, the first quarter, will reach its highest point at 1/2. And past 1, it's going to be 3/2 of a radian, or 1.5 radians. You'll reach its lowest point at negative 1/2 radians. So every sine curve has this shape. Okay? The only thing different is the scale. So sometimes the amplitude is, or the stretch factor is a 5, which basically means that the peaks are really high. And sometimes the peaks are really low, like this one is. It's only at 1/2. So, but the shape is the same. It starts at 0, it ends at 0, and it's 0 in the middle of a sine curve. And then on the first quarter, unless it's been flipped over, it reaches its highest point. in the second quarter past the half, it will reach its lowest point. So it has this shape every single time. And of course the domain is all real numbers. The range is this time negative 1/2 to positive 1/2 inclusive. Doesn't go any higher than 1/2. Doesn't go any lower than negative 1/2. So that's the shape that we're dealing with. All right, so let's look at the cosine function. Let's kind of look at the shape of that one. If we look at the cosine function using a similar t-chart, 0, we put cosine of 0, it's 1. So that first point is 0, 1. Another key point is at pi over 2. And the cosine of pi over 2 is 0. So we have that ordered pair. Pi over 2 is 0. And at pi, cosine of pi is going to be negative 1. So it's going to be at pi comma negative 1. So that's its lowest point. And then at 3 pi over 2, it's back to 0 again. Cosine of 3 pi over 2 is 0. So remember, on the unit circle, that's the x-coordinate. At 3 pi over 2, the x-coordinate is 0. So back to 0, and cosine of 2 pi, remember it's the x-coordinate on a unit circle, and at 2 pi, it's 1 revolution, which is the rightmost point, and the x-coordinate is 1. So we're back up to 1 again. So all those values can be found on the unit circle. Just draw the unit circle, go around the unit circle, and look at all the x-coordinates as you go around the unit circle. So, and that's the shape that it makes. And then when you look at that, you're like, oh, this is different than sine curve. And if you look at the period, which this is the period between 0 to 2 pi, that will look a little different from the sine curve. But if you draw a little bit more of the graph, the cosine wave looks like the sine wave in a way. Because although you're starting this one at 1 and it ends at 2 pi 1, that portion is a cosine curve. But if you look at the curve starting at, let's say, negative pi over 2 and ending at 3 pi over 2, that part of the graph is a sine curve. So if you look at just that portion of it. So if you look at negative pi over 2 to 3 pi over 2, it looks like a sine curve. So a cosine curve and a sine curve, they have similar shapes. The only difference is they are 90 degrees difference in this. So at negative pi over 2 to 3 pi over 2, there's basically a transferred graph, a transformed graph over pi over 2. And if you remember, 90 degrees, another word for that is complementary, or co-functions. So that's how they get their names. You have the sine and the cosine. So that's why cosine is named the way it is, because it's a part of a sine graph. So a cosine is part of a sine graph. It's a different view of the sine graph. So that's why the terminology is so close, and that's why cosine has the root word sine in it. Okay, so that's the idea. All right, so let's look at the properties of cosine. So the domain is a set of all real numbers, no vertical asymptotes. The range is between negative 1 to 1 inclusive. The cosine function is an even function because it's symmetrical to the y-axis. Look at the shape. The cosine function is periodic, with 2 pi is being its period. So because at 2 pi, it starts over again. So at 0, it starts at 1 and it goes downward on its downward flight. At 2 pi, it does the same thing. Starts its downward flight. All right, so the x-intercepts are at negative 3 pi over 2, pi over 2, pi over 2, negative pi over 2, 3 pi over 2, and 5 pi over 2. The y-intercept is 1, as the graph illustrates. And then you can look at the maximum values. The maximum value is a 1, and it occurs at 0. It occurs at 2 pi. It occurs again at 4 pi, because that's the period. And the lowest points are at negative 1. And it's going to occur at pi. The next one's going to be occurring at 3 pi. So it's going to be odd multiples of pi. So pi, 3 pi, 5 pi, and so on down the line. All righty? So that's the cosine function. All right? So now that we've given you shapes for both the sine and the cosine, okay, The next video, we're going to be cutting this one short right here. Next one, we're going to do some little graphs of the cosine curve. So if you have any questions on this one, feel free to contact me, and you have a good day.